Good morning, afternoon rather, March 27th, about 1:30 in the afternoon, 13:30 on the 24-hour clock. Well, we've been reading Maugin's nonlinear electromechanical effects and applications. This is it here, it's from the series in Theoretical and Applied Mechanics, Volume 1. And last time we had read to the end of Chapter 3, where it was discussed the analytic forms as regards to, after the definitions of the surface acoustic wave, the shear horizontal wave, the Bluestein-Gulyaev waves, is about their degenerates in face shear waves, as of the transverse to the sagittal plane, and is usually as in the sagittal plane, and their solutions as what follow their establishment in variables and coordinate forms and conventions of the collection of the coordinate forms and collections of the ranges of the values, thus that the arithmetic in the algebra of the operator calculus results that the products are well defined and fall in their infinite products within given ranges, that their analytical character is so defined that it so results that these analytical methods are able to then compute what are numerical methods, numerical values of these formulas of the analytic and symbolic vis-a-vis what results for the empirical or de facto as via experiment, that we're interested mostly in the fundamental theory as an axiomatic theory and a mathematical theory vis-a-vis the empirical theory, what by trial by error results that repeatability and predictability, that the experiment in the scientific apparatus, according to what we have is called science in the philosophy of science, that the repeatability of experiment and the predictive value of the configuration of experiment is a thing that the experimental apparatus is kind of like when they talk about particle physics. Say, what is high energy experimental particle physics? Well, first you want to know that theoretical particle physics is that you use the theory of springs and windings and time and manufacturing to design a watch, and thus that you have some notion of what goes into it, that according to these principles, that by the final cause of that's all parameters by time itself, that the workings of this clock, or whether it's a sundial is so designed and engineered, or a pocket watch, that here the pocket watch is the device. So that's the theoretical side. Then the experimental side in particle physics is what you do is you take a pocket watch and you shoot it out of a cannon at a wall, and you look at the springs that come out, and from this you can deduce what's inside the pocket watch. So there's much to be said for the experimental physics, because when there's a gap in the fundamental physics, or to demonstrate the reliability and the repeatability and the predictability of an experiment in its configuration by its configuration of experiment and the energy that goes into the experiment, that then the experimental is what results the empirical, where the empirical is as finally what results is like these are our formulas and these are our working formulas. Now that gets into that the utilitarian in the working formula may simply be preferable because it's utilitarian, and that the empirical is already demonstrated because only because the fundamental is lacking. Thus, as we better understand the fundamental things that go on, and that this is almost an entirely a mathematical endeavor, so that you can arrive at how mathematics works, that then the model of mathematics automatically equips the models that so assigned to the physics. that what we've been talking about in Maugin's book with regards to the nonlinear and the solutions of the systems of the harmonic functions in potential theory. And the other day I learned that potential theory, or the theory of potentials, that potential theory writ large these days is called the study of harmonic functions, which is the study of waves, which is a study for particle and wave duality and waves and resonances that these harmonic functions basically assemble as a catch-all of sorts, anything that it is. But it's to be included that it's not just the study of harmonics, but it's also the non-standard or infinite in these. That it results that the real theory of potentials is all the way out. It's the universal, the global, vis-a-vis what is that being the semi-infinite, or as where otherwise that are classical builds for these theories of harmonic functions and what is called the theory of potential, that the fields of potential theory are so modeled as of our classical milieu, the local, that it's in terms of these. So getting back to Maugin, he began his book with an outlay of the configuration space as a mathematical model, and then the variables in this and that are framed in terms of classical motion and the classical behavior of the classical electric and magnetic fields, those ones that are of Maxwell's equations particularly. And then that the Christoffel tensor was developed, and then that these waves are so defined, and that then all this has so far been analytical. It's theoretically fundamental, and in this manner, we'd say that it's theoretical physics vis-a-vis the experimental physics. So he also introduced several times notions of that, how these differ from what would follow from an otherwise naive or lacking classical concept, or that they differ from some experimental frameworks showing that in these force and couplings of the stress and strains, which are these terms we have, and that in the pre-strain of the stresses and strains and the pre-deformation of the motion and propagation equations of the waves, where fundamentally it's about the propagation of the energy of a wave, the onde in French. That thus we've got now, after the chapter 3 and some of the appendices describing some of the material coefficients with regards to the frameworks, these frames, both the Galilean frame and otherwise the invariant as about the Lorentzian frame, but also the rigid frames of these lattice frameworks of the crystallography after Christoffel, and here as he mentions Auld and Tiersten and such. That we arrive at the end of chapter 3, and that these analytical solutions have been so provided, and then we get into chapter 4 where he talks about an example of application, the waveguide convolver. 4.1, working principle of the convolver. The most used device in the application of surface elastic waves is to signal processing, where signal theory is anything to do with digital communications. It's all signal theory. Is the acoustic convolver, which allows one to work in real time while simultaneously keeping a small volume for the whole device. Here he's described it in terms of the resources of this analog device or an analog computer, that which converts a signal and information in one form to signal and information in another form. He's describing that it's possible to make it so in terms of a contained volume, whereas with regards to otherwise that you can imagine an arbitrary device that can do anything, that here he's describing a very particularly functional device that's suited to its regime, knowing the distribution of its inputs. It's possible to make optimal devices for a given input to produce a given output. And similarly in data structures and algorithms or algorithmics in computer science, which has been mostly my profession for 20 some years, and is that if you know perfectly well the distribution of the input of the data, you can actually define a data structure for it that is much more optimum then otherwise we just usually don't know the distribution of the input data, or it varies in one or another key factors of the shape and scale of the parameters, what result its distributions according to probability theory. The computer scientists may generally be ignorant of that. Then we design things in terms of asymptotics about the resources, bounds in time, the processing time, where that's in general steps of the general processing unit, or the arithmetic logic unit, or the floating point unit, or sometimes these days the graphic cards with a wide array of floating point registers, in terms of the register transfer logic and how microcode results that the signals as input as eventually as zeros and ones, and initially as zeros and ones, resulted in the machine instructions of this abstract machine that's implemented in silico. Is that it so results that the algorithms we usually work with are designed according to big O notation, or the theory of asymptotics, that the term in which they're bound in is thus to be reduced in terms of what we would usually call a constant time, linear time, underneath that being logarithmic time, and above that being exponential time, and square, and that being under square, and polynomial time generally. Thus that we range from that which is able to be done in constant time, that which is done in roots or small constants, that which is in the logarithmic, which is reducing quite a bit, and then that which is done in root, and then into the linear, and then the polynomial or square, and that may include n-bang in a sense, or the factorial, then with regards to the exponential. And then there's higher order terms of the exponential, like Knuth's notation for 2x, doubly exponential, and this sort of thing. That is what can be read from Knuth et al.'s books in the Art of Computer Programming from Knuth, which is a series of works from a lecture series in Stanford in computer science about all the concrete mathematics that goes into the digital, and the computation of all these things, and all the theory that's relevant to it, that's very well defined in terms of an abstract machine called mix, and that it involves its usual algorithms for sorting, as an example, fundamental algorithm in computer science in terms of tapes. That then there's also, besides the Art of Computer Programming, volumes 1, 2, and 3, the fascicles, as he starts to talk about graph theory and some other things, that Knuth is very famous. Then theoretically, if you discover a typo in a work of Knuth and send it to him, and he acknowledges that it's at error, he will send you a check for $88 or something like that. There's a rule for dealing with Knuth, if you can find a typo in his books. Now, if you look at it in the third volume, when he talks about Stirling cycle numbers, or rather, this is in a paper of Knuth about Stirling cycle and subset numbers, which you can find on the internet, in where there's also discussion of Iverson's APL, a programming language, where a guy named Iverson wrote a fantastic programming language, though that it involves a keyboard with a bunch of different symbolic keys for mathematics, results in about the shortest possible programs with the greatest possible oomph or power, as might often be in scientific programming or Fortran or for HPC, high performance computing. That anyways, at one point in time, at least I've felt that I discovered a typo in Knuth, but if you read for the context, it should be possible to understand what was meant by the context, and not to be led astray, and to cause an off by one error, or a sign or unit error, or something like that, which is well known why it's important to have for software engineering the formalization of these things, and theoretically, to avoid things like the Ariane disaster, which is, where a rocket blows up, or maybe less so for something like the fundamental harmonics of the Tacoma Narrows Bridge, that resulted that, according to just that it built up a resonant frequency, it tore itself apart. So those are those kinds of things that we talk about in engineering sometimes, when it helps to already have all the background of a computer science degree, including knowing the history of its usual developments of the formalizations of concrete mathematics, according to Graham, Knuth, and Potashnik. They describe these things in terms of often where the natural setting for the logarithm is log base 2. That otherwise, here, and usually for our differential in our continuous processes, the natural setting for the logarithm is log base e, where log base 2 is written lg, the binary logarithm, and log base n is written ln, the natural logarithm, and that otherwise log on the calculator key usually reflects log base 10. Thus that it's a simple means to compute how many decimal digits are in a number. So, where we talked about that being about the small volume for the whole device, that was the resources. And whereas in computer science we talk about machine resources and time, and here he's talking about analog resources, which are usually in terms of a circuit or an integrated circuit or any device you could so contrive, which results a system. Reading again from Maugin. Among the applications of this device, we note the detection and demodulation of large spectrum signals, as also the correlation of radar signals, in capital. Parasite signals are much better rejected by using a guiding propagation medium. Here the usual concept is called waveguide, and sometimes its directional apparatus is called horn. That radar, I forget what the acronym means, but it is an acronym. And when we say acronym, we still mean an initialism, or that it's read off from the terms, the first letters of the compound word or phrase that describes what it is. It's still an acronym, though it's possible to argue that it's not an initialism otherwise. Parasite signals are much better rejected by using a guiding propagation medium. His footnote reads, however, as is well known for the elastic waves, cf. Achenbach's book, the device then becomes multi-mode and dispersive in reason of the multiple reflections on the boundaries of the guide. This you might think for something as example is that if you take aluminumized mylar, like a bag of Doritos with aluminumized mylar, and you crinkle it up and you put it next to a radio device, it will reflect all these radio wave signals that are entirely random. And it's just kind of an interesting thing. So that then when Achenbach talks about the multi-mode, you can think about the multi-mode as like unwanted effects like the Tacoma Narrows Bridge that built up a resonant harmonics and a resonant frequency and destroyed itself. Or dispersive in the sense that in the dissipative and attenuative, that then there's interference of sorts in the medium that so results that otherwise the waveguide's width is a function of the frequency and the energy and the input, kind of like as we were discussing that the wave function in its solutions, according to the pre-strain and the pre-deformation of the initial values of the given configuration, the boundaries of the configuration space, that it so results these are relevant things to the engineer. Let us first examine the working principle of the acoustic convolver. We consider a crystalline substrate seen from the top in figure 4.1. On which we have been engraved two surface wave transducers, T1 and T2. Surface waves are thus emitted which propagate in opposite direction with frequencies omega alpha and wave numbers k alpha. Alpha equals 1, 2. For a linear medium, these waves meet together without interaction. They do not have constructive or destructive interference. They do not interact. They don't interact as if having any effect on each other, as you might say. However, if the crystalline substrate is nonlinear, elastic, to separate emphasized terms by the author, then quadratic nonlinearities will generate interaction components of the frequency omega 1 plus omega 2 and wave number k1 plus k2. These are some addition formula that are written out as so are describing what these interaction components have as of naturally from waves are constructive and destructive interference. These being the two things where two waves add up and they're in the same phase, then they double, and if they're in opposite phase, then they cancel. Let V naught be the usual speed of propagation, Rayleigh, or so Rayleigh's surface acoustic waves, and in his famous and remarkable example as of after Hooke's law, and Rayleigh in the solid. The wave emitted by t underscore 1 arrives at x underscore 1, that being the positional coordinate according to this time coordinate in terms of the initial coordinates being the naught coordinates, these being the 1 coordinates, at time t equals x1 over v naught, while the wave emitted by t underscore 2 arrives at t equals quantity L naught minus x1 over v naught, where L naught is the length of the, quote, interaction zone. So here, then this is the diagram that is referred to, 4.1. And as you can see here, it's got these circuits, and these are the measurements, and these are the inputs and outputs as what would be an electrical circuit, most likely. Or here is with regards to the acoustic convolver in terms of what result, the acoustic, according to the model, where we have the acoustic model that's combined with our linear model of our fluid model of the flow of electricity as has so been defined by reading Maugin here in the earlier readings. So here for that is defined interaction zone in its terms of waves and their usual properties as regular periodic motion and the constructive and deconstructive interference of waves. Figure 4.1 is demonstrated the working principle of acoustic convolver, K1 naught equals K2, where the constants K are the differences on either side here. Of these two measurements on the left and right, there's K1 and K2 are these two constants. That they're not symmetrical. Thus, that otherwise if they're symmetrical, then it would work out that there's some perfect frequency where it tunes out, say. Let E sub alpha t equals E sub alpha of exponent. And so usually in the framing of an exponent, and we're talking about I and omega, it's usually the imaginary number in Gauss's analysis, for complex analysis, exponent of the quantity I times W alpha t minus K alpha x1. So it's terms that time is time grows, that quantity grows, and as x1 grows, that quantity shrinks. Is proportional to time, inverse proportional to distance. Alpha equals 1, 2. The wave is generated by the two transducers. This is where the wave is defined by this function that reflects that according to the polar coordinate form as of the complex analysis, that what really results, that just defines the periodic motion of the wave, or its regular period and half period, in terms of which it goes one way or the other in regards to its phase, that it's so written in this way briefly. The resulting potential distribution at each point x1 in the interaction zone will have the form Vt, the velocity, equals E underscore 1 of the quantity t minus x1 over V naught times E2 of the quantity times the quantity t minus L naught minus x1 quantity over V naught. So again, proportional to the inverse proportional to x in the additive as a linear function, and inverse proportional to V naught as a multiplicative function with regards to a constant uniform in the additive and a linear in the multiplicative, as being linear in the additive. And that quantity times the exponent of, or exp function of quantity I, omega 1 plus omega 2, so as a simple sum of those wavelengths, frequency and wavelength are inverses, but they're exactly related as being reciprocals. T minus K1 minus K2 quantity x1. That relates to the above function of the waves that it describes how there's an addition formula of the wavelengths that result this value, that the potential distribution in the interaction zone is what's so defined will have this form. So thus the interaction zone is basically so defined here. Well, now that's page 1 and 2 of chapter 4, pages 146 and 147, and thus it will then continue when he starts talking about the example of this application. Here's some other books that I thought were of interest as we've been looking at these. These were the ones I picked up recently, and this Contributions to Nonlinear Partial Differential Equations helps really get into the potential theory and the harmonic things we're talking about in the nonlinear. And so we can see really that the nonlinear and potential theory are very highly related and for many the same field. This book about Markov processes, the ergodic and potential theory, and we have to talk about, or for some it's of interest, the difference between the laws of small numbers and laws of large numbers, and what large numbers mean, laws of large number mean in small terms, and what small numbers mean in large terms. And these have to do with that. In theory of probability, is that the larger the numbers, the law of large numbers basically guarantees that things with a mean will add up according to the central limit theorem, a normal distribution with a center and a mean. Whereas there's also the same kind of large numbers or laws. There's strong and weak forms of the laws of large numbers. And there's these inverses and reciprocals with regards to that in another law of large numbers, that over time in the ergodic, that there's the dissipative and attenuative, kind of as this complement has been carried in this context for a while, of the restitutive and oscillating, that we have two models together, and they represent either side of whether a given distribution basically has fundamentally the different shape. And so that's something to get into when we get into the potential theory. The potential theory is using these harmonics up above particle theory, up above particle wave duality, up above the classical impulse, up above and outside these things, building out these frameworks that allow us to then still use numerical methods, which are only the initial approximation according to the initial terms, and always have an error term, which may or may not reflect being well behaved in the sense of blowing up, or otherwise failing to maintain the expected conditions of the bounds, or that reflects the true value, of course, that these things are all put together in one theory called potential theory, and the theory of harmonic functions and the nonlinear. And it's really that something that science needs, because science needs mathematics, and it's really part of mathematics. So anyways, I got these books the other day. This one is called Path Integrals and Quantum Processes. It's by somebody named Mark Swanson. And I bought this book. He's from the University of Connecticut at Stamford, Department of Physics. It's printed by Academic Press in 1992. So 1992 is a pretty good year, and the path integral is what's called the sum of histories approach, that there's the analytic character of these nonlinear contributions that needs to be collected, and it came up out of the empirical and the experimental in the physics. And then it resulted that there's somebody like Richard Feynman who implemented some diagrams for these things that help to outlay what are the transitions of when things become a photon or this or that, or however you care to read and write diagrams, is according to Feynman. That similarly that there's the Dinkin diagrams and Kac-Moody algebras and stuff we were discussing about a little bit last time, and the theories of potential and harmonic functions, and the Hamilton-Jacobi equation, and these sorts of things. That the Feynman integral, or Feynman path integral, or the path integral, is basically referring back to an earlier discussion. We were talking about the scattering and tunneling, and how on one hand the scattering for the quantum mechanics in a continuous substrate of a continuous manifold defines how this diffusion and the dissipative and the attenuative happens in these contexts, that there's a scattering side, and so that adds up to the path integral, and that there's which is a sort of a line integral, that there's also then the tunneling side, how that adds up to pieces of analytical character, that is possible to so define it or derive it, hopefully, from the theoretical side, how that adds up to these things, that the quantum path integral then is the subject of this book. And so its contents range over mathematical preliminaries. He talks about the Dirac delta, which is not a real function. It's a function which you can envision like this. Imagine an XY coordinate plane, thus that x is horizontal and y is vertical. A function is, as you can imagine, any line you draw from left to right without lifting the pencil, without curving back on itself, without ever being entirely vertical, that is just a continuous curve. That is also a function and can be written as a sum of, it can be written as a polynomial in any given region, and it can be written as a sum of sine and cosine or any other pair of orthogonal functions in any given region. So the Dirac delta looks like a flat line all the way from the left, 0, and then on the y-axis, it goes to infinity, and it comes right back from infinity. And then it's a flat line again all the way to the right. And you might say, well, you just described a spike at infinity. It's just a flat line with a spike at infinity. But the characteristic of the Dirac delta function is that the area of that spike is exactly 1. So it's a unit area, infinite spike at the origin. So that's the Dirac delta. And how that is built is with the series of an approximation of, or a family of functions, so standardly modeling this, not a real function. Real functions don't have infinite values. As the limit of any kind of function that's got a hump in the middle, that always has area 1 and shrinks on the sides and goes up to infinity. So that's what the Dirac delta is. And it's closely related to what's called the Heaviside step function. And all the step function is a function that's a flat line from the left. On the y-axis, it steps up 1, and then it's a flat line to the right. So Oliver Heaviside and Paul Dirac are quite famous, and they're engineers and physicists first, and then their names for these things came into mathematics. Oliver Heaviside is a great guy. It'd be well to learn more about Oliver Heaviside. So, in talking about the natural units with regards to the path integral and harmonic oscillator coherent states vis-a-vis spontaneously broken symmetry, which is kind of like on the flip side of the pre-strain and pre-deformation, the inputs, what happens when those break or make an effect change the regime or reflect an effect in effect. Then he gets into Grassmann and the Grassmannians. Those are forms of hypercomplex numbers, and so we'd use them according to that they have the arithmetic properties, and so we can use them as a model in our algebras as objects. In field theory, then he gets into field theory, and he discusses, for example, symmetry in Noether's theorem, that Emmy Noether is a famous physicist whose theorem is that every invariance implies a conservation law and vice versa. So here the context is more about continuum laws, that there's a 0 in the middle, and so whatever goes either way has to approach and go either way. So we might later talk about how we can restate Noether's theorem, Noether, as not about symmetries, invariance, and conservation laws, that a symmetry implies a conservation law, but that a symmetry implies a continuity law. And then that the conservation law is superclassical as about the non-standard of these real functions. That's the way it is. That's the way it is. So then he talks about scalar field and quantization. This is kind of the opposite of when we have waves making more waves and resonances. It's like when you have waves making points of them. You're quantizing these things. You're making them a quantum value. That's how we talk about taking waves of energy and making them quantum, discrete. It's all about the continuous and discrete. So he talks about the path integral, but you can imagine that there's anything that adds up a line integral or computes the length of a line, as we've been talking about in our measure theory and according to the metrizing and Lagrangians and these kinds of things, that it's whatever works for Richard Feynman to add these up is path integral. And that's why it's really funny, because a lot of things in these days, it's like they added up and after about 5 or 6 decimal points, there's this extra contribution of only, which is, beneath, 1/10,000th of a thing. It's less than 5 orders of magnitude relevant, but it still adds up, and that gets into the levels of these experiments being concise and precise out to 29 orders of magnitude, why that is relevant. So it talks about the S matrix, that's the scattering matrix. And then we get into gauge field theory and classical Yang-Mills fields, quantized Yang-Mills fields. We want to know about Kaluza and Klein fields and Minkowski's field. And then we talk about the field occupation numbers, of which are like assigning to each point in the field a number of all the quantum properties present of the state of matter at that point. And we talk about Yang-Mills, and that's pretty premier. And then we got the Ward-Takahashi. That's pretty key. And finally, that at page 325, he arrives at deriving the Feynman rules. So the Feynman rules are heuristics, and they resulted from experiment, and it's the reason Feynman got the Nobel Prize or whatever it was he won for discovering these things. And then we talk about renormalization. And renormalization is a key concept to know about. When we talk about normalization, we talk about getting stuff back in terms of this discrete or quantum. From the wave, how is it we add back up to this quantum? And so we have to remember that normalization and renormalization only follows denormalization, or where it went through one of these considerations of the change of regime from the discrete to the constant. So we have to go through all the running variables that go through all the things that have to do with symmetries, Noether's theorem, conservation laws, and then the following these nonlinear contributions of the potential theory, which add up to this surface, that on the other side of the surface, as it were, then this renormalization occurs, that's what allows us, that's the value we predicted, or the value that we can control, because it's in terms of that detector, or what it is on the quantum side, again, from the originally quantum, the continuous, and then back to the quantum again. That the next section after deriving the Feynman rules is renormalization. Then in chapter 9, he reads off some various numerical methods. Well, that'll be interesting. Something to look at a little bit more later. And then this here, this is geochemistry of solids. This is a great work. This is great for anybody who needs a quick refresher on inorganic chemistry, which is basically any matters of chemistry that don't involve benzene or organic compounds. So Geochemistry of Solids by W.S. Fife of the University of California, Berkeley, is a McGraw-Hill Book Company book published in 1964. And what he provides is, in the first 10 or 15 pages, about the first 30 pages, an excellent introduction to atomic theory and the reasoning why we have orbitals of the electrons, and how and why the forces of the positive nucleus of protons and neutrons in our atomic model, and the negative charge of electrons, how it so is that they rotate where they do about the nucleus, thus they don't fall into it as they share charge, and that thus in surfaces and it's so modeled that all of what results, all the stoichiometric formulas of chemistry, given temperature and pressure constant, and not talking about radiochemistry or nuclear chemistry, where the central dogma of chemistry that substances are defined by their elements of matter, as according to the periodic table of elements, which carefully describes in thusly graphical detail how the various orbitals are so derived, so that it's possible to predict for a given substance its properties of chemical bonds to other substances, and the reactions that they may so follow, that according to stoichiometry, that what goes in must come out, the conservation law of mass, that all these elements according to the atomic number and the associated neutrons of an atom, thus its mass in terms of moles by Avogadro's number, 6.02 times 10 to the 23rd, an arbitrarily large number of these atoms that are basically built off from the observed mass of the electron, and 1 AMU, what is called an atomic mass unit. This book is a great introduction to that, and I might look to that a little bit later. Well then, that's what's reading for today. See here, 41 minutes, 41 seconds. Good afternoon.